Hi, and welcome to 12 SDD, Option 2, Lesson 9, Very Large and Very Small Numbers in Binary, or IEEE754 Single Precision. Here are the syllabus dot points, pause if you'd like to read them. So this will look at a few things. We'll start off with fractional numbers in decimal. Okay. So to understand how fractions work in binary, we need to first look at how they work in decimal. Here's the place value table we normally work with. We've got 10 to the power of 0 is 1, 10 to the power of 1 is 10, 10 to the power of 2 is 100, 10 to the power of 3 is 1000. And we understand to get bigger numbers, we can keep adding columns on the left side of this table, and each column will increase by a power of 10. So the next column we add will be 10 to the 4, which is down here, which will be 10,000, or 10 to the power of 5, which is 100,000, and we can keep going, 10 to the power of 6 to be a million, and so on. However, we can also go to negative powers of 10, which go on the right side of the table, and these give us tenths, hundredths, and so on. So we've got the normal place value table here. There's my decimal point. And so 10 to the power of minus 1 is 0.1. 10 to the power of minus 2 is 0.01. 10 to the power of minus 3 is 0.001, and so on. These columns can be added whenever we need them, depending on how big or how small the number is that we want to represent. In each case, the numbers go up in powers of 10 as you move to the left, and they go down in powers of 10 as they move to the right. And this works the same in binary. So here's the standard place value table we use, and if we want to keep going up, we go to 2 to the power of 9, 2 to the power of 8, which is 256, 2 to the power of 9, which is 512, and so on. If we want to go fractional, we can go to the right, 2 to the power of minus 1, which is 0.5, 2 to the power of minus 2, which is 0.25, and so on. So in this way, we can represent 0.5 base 10 as 0.1 base 2. 3.75 base 10 as 11.11 base 2, 17.125 base 10 as 10001.001 base 2. But how do I represent 0.1 base 10? We can use a converter, and I cheated because I did, and it converts to this, 0.000, and you can read the numbers there. The problem is that this conversion is truncated or rounded, because if I then take this number and convert it back to decimal, I get this, which isn't 0.1. So the problem is that it can't do it exactly the same way. It's not going to be exactly the same number. And so the point I'm trying to make here is that conversions from binary to decimal and vice versa are not always easy. Sometimes they don't work perfectly. You'll also recognize that this takes up a whole lot more memory than this does, and so there's a better way. So we use scientific notation. And to understand how to represent big and small numbers in binary, we need to first look at how it's done in decimal. We do this using scientific notation. Instead of representing a really big or a really small number as the true number, we represent it as the multiplication of some fraction and 10 to the power of something. So for example, I looked up on Wikipedia the diameter of a human hair, and it varies from 17 to 180 micrometers. If we take 17 micrometers, that equals 0.000017 meters. And this is 1.7 times 10 to the minus 5. And this is calculated by calculating how many times the decimal point moves and in what direction. Right is negative as numbers are getting smaller, and left is positive as numbers are getting bigger. So if I've got 0.00017 meters, and if I move it 1, 2, 3, 4, 5 to the right, I get 1.7, which is what I had before, and therefore I've got minus 5. So let's assume I wanted to represent a much larger number, and I wanted to use the number I've got below, which is something I just made up. Obviously, we'd need a whole lot of memory to represent this number, okay? And the problem with that is the only thing that's different is the first 7 numbers, all right? I can represent this number exactly using scientific notation. And if I remember that there's a decimal point at the end here, so it's all of this, 0.000, we can count how many places it needs to move to get to the front. I did this, and I found out it was 69, and so our number is actually 1.076554 times 10 to the power of 69. This would obviously take less memory to store, because all of these components are a lot smaller than writing all this out. And so the Institute for Electrical and Electronics Engineers, the IEEE, they recognised this would be a problem, and they developed a standard for representing very large or very small numbers in binary, and therefore the standard by which computers would handle them. And they came up with IEEE754, which is the single precision floating point representation. It uses 32 bits to store the data and is divided as follows. So the first bit is the sign bit, and it's either 0 for positive or 1 for negative. The next 8 bits, bits 2 through 9, are the exponent. And so it's the power of 2 that you'll be multiplying the rest of it by. Alright, so this might be 2 to the power of 3, 2 to the power of -5, etc. Okay, and this is stored in XS127 form, meaning that the number here is represented when it's minus from 127. So if I've got 100, if I put 128 here, I then take this number, which is 128, minus 127, and I get the true exponent, which is 1. Okay, and we'll see an example of that in a minute. The F is the fractional component of the mantissa. So the mantissa is the 1 point something. So if I go back to here, this bit's the mantissa, and this bit obviously is the exponent. Okay, so we assume that the mantissa will always have 1 point at the front of it, and so we don't store that. We only store the stuff after the decimal point. So here's an example of a number I prepared earlier. All right, here's my number here. The first bit's the sign. This is a 1, and this will be a negative. Okay, this bit here, that equates to 131, and so I minus 127 to get 4. This bit here, all right, in binary, works out to be 1 times 2 to the power of -1 plus 1 times 2 to the power of -2, which equals 0.75, sorry. And so I stick it all together, and I get minus 2 to the power of 4, the exponent there, times 1.75. And so that'll be 16 times 1.75, which equals minus 28 base 10. Another example, okay, we have 0, which is positive. We then have an exponent here, which is 3. So 3 minus 127 would be minus 124. Okay, we have the mantissa here. So 1 times 2 to the power of -1 plus 0 times 2 to the power of -2 plus 1 times 2 to the power of -3, which is a half, plus 0 plus 0.125. So we get 0.625. And so this is going to be positive 2 to the power of minus 124 times 1.625. And as there's heaps of zeros in that number, you don't need to go any further than that. You could sit there and write out 124 zeros if you want to, but there's no real point. So I'll now detail how to convert from decimal to binary. And in this example, we're going to be using minus 3.24. The first thing we do is we work out the sign and set the first value. So sign is minus, as a sign is negative, the first digit is going to be a 1. And you can see all these ones are x's because we haven't filled that out yet. Then we need to calculate the exponent. And to do this, if the integer part of the number is greater than 1, work out which positive power of 2 divided by your number gives you an answer of 1 point something. If the integer part of the number is 0, work out which negative power of 2 divided by your number gives you an answer of 1 point something. And if the integer part of your number is 1, you're already done, and your exponent will be 0. So for this problem, we need to calculate the exponent, and this is the relevant part. The integer part of the number is greater than 1. So 3 is greater than 1. So we work out which positive power of 2 divided by your number gives you an answer of 1 point something. Okay, so minus 3 divided by 2 to the power of 1 gives you 1.62. Okay, we've already got a 1 point something, so that's it. My exponent's 1 because I divided 2 to the power of 1 to get to there. Now, you'll notice I haven't done anything over here yet. So I now need to work out the exponent in IEEE form. Okay, so this is represented in XS127, meaning we need to write our exponent in such a way that if we subtract 127 from it, we get our exponent. So for us, we'll need to have exponent minus 127 equal 1. Therefore, our exponent will be 128, as 128 minus 127 equals 1. Converting 128 to binary, we get 1 with 7 zeros, and that becomes my exponent there. And now we need to work out the fractional part of the mantissa. And to do this, we'll use the value we calculated in step 2, which is 1.62. All right. And this is pretty simple, but can take a long time. We basically we multiply the fractional component by 2. If the answer is above 1, we write a 1. If it's not, we write a 0. And we continue until we get 1 as an answer with no fraction, or we hit a pattern. For this purpose, we should always write down the fractional component so we can recognize a pattern. So we take 1.62 and we ignore the integer. So we look at 0.62. 0.62 times 2 equals 1.24. As the answer is above 1, I write 1 here, and I move to the next digit. Okay, we take our answer from before. So our answer is 1.24, and we ignore the integer, so we ignore the 1. So we have 0.24 times 2, which equals 0.48. Because that's not above 1, I record a 0 in the second fractional spot. I take the answer, 0.48. I ignore the integer. So 0.48 times 2 equals 0.96. It's not above 1, we record 0. I'm going to keep doing this process in a table form, okay, like this, so it's a lot easier to see. So take 0.96, ignore the integer. So this one is above 1, so I write 1. Take the answer, 0.92 times 2 is 1.84, that's above 1, I write 1. 0.84 times 2 is 1.68, that's above 1, I write 1. 0.68 times 2 is 1.36, it's above 1, so I add 1. And so on as we go. I'm not going to read the rest of them out, but I will present them slowly so you can see the answers. So there's that one, and that one, and that one, and that one. And so we write 1 there, and a 1, and a 0, and a 0, and a 0, and a 0, and a 1, and a 0, and a 1, and a 0, and a 0, and a 0. And so we didn't get a pattern, we didn't end on a 1, and so we haven't finished with a perfect division, meaning that this approximation, this number here is only an approximation of minus 3.24. The computer can't actually represent minus 3.24 exactly using IEEE single precision. It's possible using another form it could, so maybe using double precision it could do this, but I haven't gone through and looked at that, so I don't know if it can do that properly or not. It might be that representing this number in an approximate form is okay, but if you're doing scientific experiments or calculations and you need very precise measurements, this may not be enough precision for those.